Well, hello, come on in and welcome to the GameDev Tavern, a cozy little corner of the internet where we create fun, tiny little games from scratch. My name is Nicholas, and this is the third episode in the intermediate series where we create an arcade soccer game in Godot. So, in the last episode, we started implementing a very basic state machine using if statements, and we discussed the limitations that come with that approach. In today's episode, I'm really excited to drill into core architecture choices with you. Let's go ahead and talk about state machines. So, typically in Godot, every node is meant to be independent of their parent. For example, here in our current player scene, the sprite, the animation player, and the collision-shaped nodes don't need to know about the player-parent node. And this coupling is actually really great. It allows for clean communication between the various components of that scene. Typically, in Godot, a parent will call methods from its children, but children will only send signals upwards that can then be caught by the parent. A call down and signal up is a sound principle of using the Godot engine. However, there is a common misconception around design patterns that they should always apply regardless of the circumstances. And just remember, design patterns exist to help solve specific problems, but they come with their own set of trade-offs that need careful consideration. So in our case, when a class gets too big, it can actually be a good idea to break that design principle and break down that long logic to disperse it amongst child nodes. Another very valid use case is when entities don't share much in common, definitely not enough to inherit from the same parent. So rather than force an awkward inheritance model of those objects, it's actually much better to simply write the behavior logic that is specific to that common trait in a separate node and then instantiate that node as a child object. For example, here we have an enemy and a house. Both of those can be clicked to be focused by the player. That behavior should only exist in its own node and shouldn't be part of the house or the enemy objects themselves. This is actually so common in game development and actually in software engineering in general that by default, it's usually better to prefer the composition model over the inheritance model. I think Unity's engine is actually a bit more adapted to this, as one object will typically have multiple mono-behavior scripts attached to it, and each of the scripts can describe a trait that can easily be shared amongst other objects. That said, it's absolutely doable in Godot as well, and in fact, I've actually seen multiple ways to implement a node-based state machines in Godot. And you've probably seen some of those things on the internet as well. But the main ideas remain the same. Basically, all of the logic for a given state is done within the script of a dedicated child node. And that child node pilots the parent and updates its attributes. So the parent doesn't need to know about its state, and it doesn't need to do any sort of logic there. And the last condition is that the parent can only have one active state node at a time. So I actually have seen multiple flavors of this node-based state machine on the internet, and you might have as well. So I wanted to take a minute and just discuss the various alternatives alongside the pros and the cons. Once again, for all those types of architecture design patterns, you're always going to have multiple alternatives, and it's always good to weigh the trade-offs and then just see which one you think fits your use case best. So the first variant that I saw, the developer added all of the possible states to the parent object. So basically here, as part of our player object, we would have a state machine, and then as a child of state machines, we would have all of the states. And this means that you can create that object right from the start, having all of its state ready. Throughout the life cycle of the parent would disable all of these states except for one. The main benefit here is that objects look the same. The structure remains fixed throughout the game. There's no need to create or move nodes around. It's very predictable. It's very memory efficient. The main drawbacks are that the node structure actually doesn't guarantee that a single state node is active at a time. This is something that's done in code, but given the fact that you have multiple nodes, it's always possible that you have two state nodes that are active, in which case you would be processing the logic for multiple states at the same time. This is absolutely something that you want to avoid. And then also enabling and disabling the same nodes that are currently instantiated as child objects means that whatever data existed when you exited a state still exists when you enter it again. there's this, this data persistence between those entry and exits, and it's usually not something that we desire. It can actually lead to tricky bugs that are very difficult to debug. The second variant that I've seen is kind of similar to the first one, except that all state objects are kept in memory. So this time, they're not instantiated and added to the state machine object, but there's only a single one that gets added as a child. And this solves the guarantee issue of having a single state that is active. It's also very memory efficient because you never get rid of those objects. You always keep them in memory. However, you still have the same problem that when you enter a state that held information from the last time you exited it, it can cause issues if you're not very careful. So the third variant is actually my personal favorite, and that's the one that we'll be implementing in this course. So it's very similar to the previous variant in the sense that only one child node exists, but rather than keep it in memory, we will actually instantiate it every single time we switch states. This will make it super predictable when we enter and we exit a state, and the code will actually be quite cleaner in my opinion. Now, I'll hand it over to you. It's definitely much less efficient, memory or CPU-wise, than the first two variants, given the players will actually be switching states very regularly, and so we'll have to instantiate and recreate the same state nodes multiple times throughout the game. But keep in mind that creating and adding simple nodes like this in Godot is actually extremely fast. And premature performance optimization is always quite a thorny area. It's actually much better to start optimizing for performance when you actually see performance issues. So what will that actually look like? Well, our state nodes are going to be very simple nodes. We're going to have them inherit from the node object, and all of our states are going to share a bunch of things. So we're going to have a base common class, which will serve as a base class for all of our states. This base class is going to be called player state, and they will contain things like a reference to the player object. They will have the ability to transition to a different state using a signal. So we'll be creating that node that the other states can inherit from. Finally, for each new state, we'll have a inherited scene or inherited class called move state or tackle state. And each of those will have separate logic for when we are inside that state. In the enter tree, we'll include logic meant to be executed once we enter the state. So when the node is added to the tree, we'll execute that code. And in the exit tree, we'll include logic meant to be executed just once prior to switching states. Whenever the node is being processed by the engine, the state will have access to the player property and be able to alter its properties directly until it's ready to transition to a different state, at which point it will actually trigger a custom signal for this. Now, from the player standpoint, we'll simply need to create a new state node every time we enter a new state. So we'll ensure that we remove the prior state node as well, just to make sure we only have one, and then we'll have to listen to its request to transition states. So the player doesn't need to do any custom logic itself. It's always going to delegate that to whatever state node is currently active. And the process method, as a result, is going to be quite empty. This is a good thing because we'll be able to decouple the logic and make sure that it's only being included in whatever state it needs to be executed. All right, so that's a lot of talking, and I'm sure that I'm probably confusing you more than anything. So let's go ahead and put this in ones and zeros. And don't worry if you haven't grasped everything yet. We're going to be building a bunch of states down the line, so it will really start to click and become second nature to you as we start adding more and more of those states. So let's go ahead and hop into the code, and we'll start by adding some of this code. I'll make sure to wait every single time to make sure that you have fully understood what we write. All right, so let's hop back into our player script, and we will start by adding an enumeration for all the various states that we have. So let's start with moving and then tackling. Okay, and then we'll need to create our base class for the various states. So let's go ahead and create that within file new script. And let's see, where are we going to put this? Let's go into scenes, characters, and let's actually create a new folder here. We're going to put all the states inside that folder. Let's call this character states, and we are going to call this player state. All right, we'll give this a class name. And a couple of things that will be common across all the states which we'll inherit from this class. First of all, we need to have a custom signal to indicate that we want to transition states. So we'll keep the paradigm of signaling upwards, right? Like these state nodes will be children of the player scene. So we just want to be able to signal upwards whenever we need to change state. The common practice in Godot is to use past tense for signal names. So let's just call this state transition requested. All right, and here we'll just pass in a single argument, which is going to be the next state, the new state, and we'll have that be an enumeration of the player state. Next, we'll need to have a reference, like every one of those states will need to have access to the player so they can modify the properties directly. So we're going to have a reference to the player here. We'll set that to null initially. And then we are going to create a method that allows us to set up these state nodes. And we just need to basically fill in the content of this player here. So let's pass in context player, and we'll just set this up. So the state nodes here, because they're children of the player, they need to know about that object, and they'll be able to alter it directly. And this is going to be it just for this base nodes. I'm just going to wait for a few seconds so that it makes a lot of sense. And over time, whenever we will set up those nodes, we'll be adding any sort of additional dependencies that we want to inject here. We'll talk about that in a little bit more details down the line. But just for now, hopefully you understand that whenever we create a node, we'll need to call the setup method, pass in the player so that these state nodes can then access the player. So let's go ahead and create our inherited states nodes. So let's start with moving. So let's go ahead and create a new script. Let's make sure that it's part of the character states folder. I'm going to call this player state moving. Let's give it a class name. I guess moving is fine. All right, so here, there's no logic when we enter this state, but we will want to copy and paste some of the logic that we had in the player code. So let's go into the process method here. We won't be using this delta. And here we can actually reuse some of the code that we wrote here. So let's go ahead and let's copy all of this for now. Okay, and go back into the player state, the player state moving, paste this. All right, so here it's complaining that it doesn't know about those variables. This is normal because those variables and those properties belong to the player. So we'll need to pass in the, we'll need to call these as part of the player. So again, this is kind of breaking the paradigm of never having to call the parent. In the case of node state-based machines, this is something that we actually want to break. All right, so what is it complaining about? Player is not declared in the current scope. Oh, because we need to extend our player state. There you go. Okay, and then here we'll call player.handle human movement, player.set, and player.set heading. And let me think. So here, I think human movement, we should actually probably take the code from the player and bring it here. So let me cut this and bring it over here. And then let's remove this code here. All right, and this should work, except we just need to pass in the player.control scheme. And then here we want to set the player velocity and the player speed. Now we also want to add the logic for transitioning into the tackling state. So here we'll just check if the velocity vector is, if player's velocity is different than vectors.0, then utils.isAction just pressed, and here we'll have player.control scheme, and we'll want to press the shoot key, in which case we'll be able to transition. So let's go ahead and call the signal state transition requested, and we'll emit that signal with the tackling state. What is it complaining about? Oh, it's vector 2.0. So let me go over the code real quick. So this node here is going to be added as a child object of player, which means that this node is going to be processed on every single frame. This node will do all of the logic for moving the player by just referencing the player directly. Remember that this has been done as part of the setup. And then we want to be able to transition into the tackling state. So note that you can only do that if you are part of the moving state, right? This logic is specific to the moving state. So this ensures that the transition can only be done from that state. And here we just check whether the velocity is different than 0, meaning that the player is actually moving, and if we are pressing the shoot key, in which case we'll transition over to the tackling state. We'll need to catch that signal, by the way, in the parent and just handle that logic. We'll do that in just a few seconds. For now, we can go ahead and implement the tackling state similarly to what we had done initially with the if and switch statements before. So let's create another class. And I'm going to also place this in the same character states folder. I'm going to call this one player state tackling. Give it a name, tackling, and let's extend our player state. So we have access to everything, including the player. And here we're going to paste some of the content that we had typed earlier. So here, duration tackle, we had mentioned 200 milliseconds. I think that worked well. We wanted to keep track of the time where we start tackle. We started tackling. We'll just set it to the current timestamp to start with. All right, and so when we enter the tree, so when the node gets added, which means we're starting to transition into this state, we'll want to play our animation called tackle. All right, and here we don't have access to the animation player. So there's two things we could do. One of them would be that we could simply call player.animationPlayer. Another one that we could do, which is something that is probably favored, is by doing this, you basically create a hard coupling between the player and the animation player. And while this is okay, I mean, we're not going to be changing this for quite a bit. It's actually sometimes better to inject all of the dependencies inside the state object directly so that you don't need to have those hard references. So we're going to do that right now, and we're going to be doing this for all of the dependent objects of player. Rather than calling that directly as a property, we're going to go into the setup. We're going to have a reference to our animation player. And we're going to pass it as part of the properties when we set it up. All right, and then let's just set the proper value. All right, and so now that we have this, we don't actually need to tie in to this player.animation player because we now have a reference to it. And this is actually much cleaner. It actually helps a lot whenever you do testing. There's a lot of dependency injection frameworks out there like Juice and Spring, and just there's a ton of it. It's a very common pattern that really helps decoupling things. So we'll be using this down the line, and I'm not going to go too far in depth there, but just know that when you you want to set up a node that has some dependencies, it's much better to decouple those dependencies from one another. Okay, so here when we're entering the tree, we want to play the animation tackle, which is good. We also want to set the value for the start tackling. We actually don't quite need this because we're setting this when the node gets created. So I guess this is more of a bonus than anything. But yeah, you could potentially remove this line and I think you should be fine. All right, and then in the process method, I don't think we need delta here, so let's just put an underscore. We just want to check whether we spent enough time in this state. If we did, then we'll want to transition into the player's moving state. All right, so I'll just wait a few seconds here just to make sure that everything makes sense to you. So this is a logic that will get executed when the tackling state will be added as a child node of player. Whenever it gets added into the tree, we'll start playing the tackle animation. We keep track of time, and then as long as it's in the tree here, it's going to execute this process method every single tick. And if we've spent enough time inside this node, then we'll transition over to the moving state. Now remember that when we do this transition, the player's role will be to delete this node from the tree and to create a new node for the moving state. Okay, so let's go ahead and implement this. We need to have the player start to create all of those nodes every single time we want to transition nodes. So rather than have that logic as part of player creating nodes, all the time, we're actually going to delegate this to a different class. Let's go ahead and create a new script once again, and let's place that inside our character script. I think this is better, and we'll call this player state factory. So the factory pattern is something you'll hear about quite a bit. It's basically just a class who's meant to create objects and return them. So it's a fancy term for something that is actually very simple. We'll give this a class name. We'll call this player state factory. And it actually don't even need to extend nodes. This is just going to be a very simple object. So let's go ahead and create a dictionary of all of our states. So for moving, and here for the keys are going to be the state, and the values are going to be the various classes. So here we have the player state move and player state dot tackling. We'll map it to the tackling node here. Okay, so we have initialized that dictionary. Now we'll just have a single method, and this is going to be very straightforward. Get fresh state, and we'll pass in a player state, and it's going to return a player state. So be careful here, there's no dot, because here we're returning an instance of player state. It can be either the moving or the tackling state. Both of those inherit from player state, which is why we can just specify the base class here. All right, so first thing that we should probably do is make sure that we contain these states. If we don't, we'll just throw an error for now. All right, and otherwise, we'll get the class from the dictionary, right? This is going to be the class, and we'll just create a new one. We'll instantiate it. Okay, so the player can just use this player state factory to just request a new state object every single time, and then he can just add it to as a child. But all of that logic of just creating the right state, we can just put into a different class into this player state factory. This is a nice, handy thing that we'll be doing for node state machines. All right, so back into the player here, we now can track of the current state. So this is going to be a node, and by default it's going to be null. And we also want to have a reference to our state factory. We'll just instantiate it once. That way we can then use it throughout this class. Okay, we'll need a method to switch states. So let's go to just below the process method here will be fine. Switch state, and we'll pass in a state as an argument. It's going to be a state. All right, so what do we want to do here? Well, first we want to destroy the existing state if it already exists. So if the current state is not null, let's go ahead and remove it from the tree. We want to make sure that it disappears from the list of children here. Then we want to create a new state. So we'll go ahead and get it from our state factory. And we'll pass in state here. And then we'll go ahead and set it up. So it needs two arguments, and we'll just pass in the player and the animation player. Next, before we add that node, we'll need to connect to the signal. All right, and actually that signal, whenever we transition state, we actually want to reconnect to this exact switch state method here. So we'll just bind it. All right, and in the ready function, let's go ahead and switch state to state.moving. All right, and finally, we'll just do two quick handy things. First of all, we'll give that node a special name. We'll call this player state machine. And then let's add the name of the state as a string. So it's going to be a node that appears here called player state machine, comma, and then it will have either moving or tackling. So that will be good. And then we just need to add that node as a child object. So call deferred. What we want to do here is, actually, I think we can do add child current state dot call deferred. Oh, I guess not, huh? All right, so call deferred, add child of our current state. All right, and this ensures that because we're modifying the tree, it doesn't interfere with removing that state. So this I learned by mistake. You know, I originally added the child and then just complained about it. So you can try it without. So when we start the game, it should add the moving state as a child object. We're going to try this right away. So let's go ahead and press F5. And I'm going to take a look at the remote view here. I don't know if you'll be able to see it because it's going to go pretty fast. But this here, this 0 should turn into a 1 whenever we tackle. So let me bring this back here. And I'm going to move. And when I press the bracket key, oh, well, terrible. Let's see here. All right. Try to see if you see this 0 turn into a 1. Okay, maybe you saw it and then it just turned back into a 0. It's quite temporary. I think this view doesn't update all the time. But you can see here what happens is that we only have a single node for the state machine and it swaps it for the tackling state whenever it needs to. All right, so while the results actually look the same, the code logic is now well spread amongst the various state nodes. The best thing about this approach is we can add a ton more complexity to the player object without creating any sort of complex classes. And the player class is actually going to remain extremely simple. I mean, throughout the entire series, we're probably going to add maybe 20 more lines of code to this class. So we now have a working node-based state machine. Everything seems to be working well. I'll just try it again with the player 1 as well. Making sure we can tackle player 2. All of that seems to be working well. What do we typically do when everything works well? Well, we just save our changes. So let's hop over into Git real quick and let's bring our UI. We've got a bunch of new changes here. We'll just add everything and let's commit under, added node-based state machine. All right, this is really great. We're making great progress here. And I want to use the last few minutes of this episode to illustrate how easy it is to add a new state. So currently, you may have noticed that tackling is a little bit broken in the sense that you can repeatedly press the tackle button and the player will just continuously tackle. This isn't really something that we want to do. By the way, you can see that the voice sorting is broken. This is also broken. We'll be fixing a bunch of those things down the line. But for now, let's just go ahead and ensure that we cannot tackle repeatedly and that we have some amount of pause between the tackles. So to do this, we're going to introduce a new state called recovery. And we'll transition into this recovery state after we've gotten hurt or after we've performed some form of special action like a tackle or a power move. So the process for adding a new state is going to be the exact same for every single state that we're going to be adding, and it's going to become very familiar to you as we add more and more of those states over time. So let's start by adding an animation. So hop over into the 2D view, bring in the animation player. Let's create a new animation. Let's call it recover. And this is going to be a single frame animation, so let's make it last 0.1. Set the snap to 0.1 as well. And I guess we can loop the animation and hop over into the player sprite. You want to pick frame 18 and just hit create on the keyframe here. All right, so now we'll want to next add that state to our enum. So let's hop over into the code, and in the player script, let's go ahead and add the recovering state. We'll need to create a new class to represent the state. So file, new script. Let's go over into our character states folder. This is great, and we'll call this player state recovering. All right, this is going to look exactly like what we did for tackling. So let's give this a class name. Let's extend player state. And here we'll need to know for how long we need to recover. So let's just have a constant duration recovery. We'll set it to half a second for now. We'll need to keep track of time. And then when the node gets added into the tree, so when we enter into that state, we'll want to set the time here. So again, I'm not sure that this is absolutely necessary because the delay between the object being created and the node entering the tree is going to be very small. So you probably might be able to get away getting rid of this. But okay, then we'll want to set the player's velocity to 0 when we're recovering. Don't want them to keep sliding. And then let's go ahead and play our proper animation. By the way, all of those animations have like those strings. This is really not ideal. It would probably be better to have some form of dictionary, global dictionary that has all of those. But anyways, you feel free to do that. It's probably going to be cleaner. And then in the process method, the only thing we'll need to do is just to make sure that we have spent enough time inside this state. So if time.getTicks, minus time start is greater than duration, then we will want to transition states. Let's go into the moving state. All right, and so just waiting a few seconds here just to make sure that this makes complete sense to you. So basically we're entering this new state, we're playing the animation and waiting until we've spent half a second, and then we're transitioning back into a different state, which is the moving state. So this is great. We'll want to do a few tweaks. First of all, when we were tackling, rather than bringing us into the moving state, we'll hop over into the recovering state this time. And then we'll want to make sure that the player state factory knows about this state. So let's go ahead and create a new key and value here. Recovering, player state recovering. There we go. Okay, so let's go ahead and try this out. And we should now have 500 milliseconds. There we go, between the moment where you can actually do another tackle or move again. Okay, and you can try that with the second player. And okay, well, once again, what do we do when we have a working state? Let's actually clear the, I see some warnings here. I do like to clear those warnings, making sure that those things are clear. So this delta parameter, we're not going to be using, we can get rid of. This signal here is declared but not used. This is actually something that we want to ignore. This is a valid use case where we want to define the signal as part of the base object, and we want to only use it as part of the inherited scenes or inherited objects. So we can actually ignore that. We can do this inside our project settings and hop over into the debug section, hop over into GDScript, and you want to scroll down to unused signal. Let's just go ahead and ignore this. All right, so if we press F5, we should now have no more warnings, which is good. We have a working state. What should you do? You should, of course, persist it online. So git add a git commit added new recovery state. And let's persist this to the internet. All right, and this is going to be it for this episode. I know we're a little bit out of time and there's a lot of code in here. So, I'm trying to move fairly fast because we do have a lot to cover. So if you have any questions about anything that we did today, please don't hesitate to add a comment below and I'll be sure to respond quickly. Node-based state machines are just super helpful. When you have complex objects, And I mean, they're actually very helpful for even simple objects as well. We'll probably use that across the board inside this course. This is something you can take to any game engine, and it will work for any type of game. So it's a very helpful pattern to understand and master. And I strongly encourage you to revisit any of the code that we've written here, just to make sure that you fully understand. So that being said, I hope you learned something useful today. And if you enjoyed this tutorial and you want to see more free courses like this on YouTube, please hit those like and subscribe buttons. Let the magic of YouTube algorithms work in my favor. Thank you so much again for watching. Time to take a quick break, and I'll see you in the next episode. Cheers!